Put a uniform meter scale horizontally on your extended index fingers, with the left one at 0 centimeter and the right one at 90 centimeter. As you slowly move both fingers toward the center, something strange happens. Only one finger slips at a time. First the left, then the right, then the left again, until both meet exactly at the 50 centimeter mark. No matter where you start, both the fingers always end up at the center. Strange, isn't it? Like, first of all, why not slip together? And secondly, why always the center? Well, this exact situation was asked in JEE Advanced 2020, Paper 1, and they didn't just want to know what happens. They asked where it happens, the exact points where the fingers switch roles. Honestly, it's one of the most underrated JEE questions ever, and the physics behind it is just beautiful. Let's now simplify the setup and shift our camera to a side view. Imagine the meter scale resting on your index fingers, with your fingers pointing into the screen. Let's say the left finger is at a distance x1 from the center, and the right finger is at a distance x2 from the center. The normal forces exerted by the left and right fingers are N1 and N2, respectively. Now let's draw the free body diagram of the scale. The scale is at rest, so it must be in equilibrium. First, we write the force balance in the vertical direction. N1 plus N2 equals mg. The combined normal forces balance the weight of the scale. Now for rotational equilibrium. We'll take torques about the center of mass. Remember, torque equals r times F times sine theta, where theta is the angle between the r and F vectors. Since both N1 and N2 act vertically, and the scale arms are horizontal, theta is 90 degrees, and sin theta is 1. Let's assume clockwise rotation as positive. The torque exerted by the left finger is x1 times N1. N1 tries to rotate the scale clockwise, so it gives positive torque. N2 tries to rotate it anti-clockwise, so it gives negative torque with value x2 times N2. Equating the net torque to 0, we get x1 times N1 equals x2 times N2. Now from these two equations, we can find N1 in terms of distances. And we discover that N1 is a decreasing function of distance from the center. That is, as the left finger moves toward the center, x1 decreases, which in turn increases the value of N1. This is an important result. Now let's talk friction, the heart of this problem. Remember, kinetic friction cannot adjust itself, but static friction can. This means in the absence of any external force, static friction is 0, but in the presence of a force, it acts equal and opposite. However, if the applied force exceeds the maximum static friction, the block starts to move. Also, kinetic friction is always less than maximum static friction. At any moment, only one finger is slipping. Let's assume the left finger is sliding and the right finger is stationary. That means the left finger provides kinetic friction, the right finger provides static friction, equal in magnitude to the kinetic friction provided by the left finger. Also, the directions of both friction forces are opposite to each other, because the scale is in equilibrium in the horizontal direction as well. Now remember the result? As x1 decreases, n1 increases. The kinetic friction force here is expressed as F1 equals mu kinetic times n1. So, as n1 increases, the friction due to the left finger increases. That means, as the left finger slides toward the center, the kinetic friction increases, and so does the static friction on the right side. But after some point, this kinetic friction exceeds the maximum limit of static friction, and the right finger fails to keep the scale at rest. To maintain equilibrium, the left finger comes to rest, adapts to static friction, and lets the right finger slide by switching to kinetic friction. Now the left finger is the one adjusting its friction, equal to the kinetic friction provided by the right finger. And this cycle, mathematically, at the point of switching roles, kinetic friction of the left finger equals the maximum static friction of the right finger. That is, mu kinetic times n1 equals mu static times n2. From the earlier equations, we know x1 times n1 equals x2 times n2. Substituting and simplifying, we get mu kinetic times x2 equals mu static times x1. This equation governs the position at which the fingers switch their roles, and this is exactly what JEE Advanced expected you to figure out. Also notice that if the fingers cross the center and land on the same side, that would create a non-zero torque, which disturbs the equilibrium of the scale. That's why the system doesn't allow the fingers to cross the center, so they always end up meeting exactly at the center. Now, coming back to the JEE Advanced question, it's all very clear now. It's stated that the left finger is at the 0 centimeter mark and the right one at the 90 centimeter mark. That means initially the right finger is 40 centimeters away from the center and the left finger is 50 centimeters away from the center. Now the left finger slides while the right finger is at rest, which means x1 changes and x2 remains constant until the fingers switch their roles. So, at the point of switching roles, maximum static friction provided by the right finger equals kinetic friction by the left finger. Using the relation mu kinetic times x2 equals mu static times x1, and plugging in the values, we find x1 equals 32 centimeters. That means the left finger stops slipping when it is 32 centimeters from the center, and then the right finger starts to slide. Now, during the interval when the right finger is slipping, x1 remains constant and x2 changes. At the next point of switching roles, the question states the right finger is at a distance xr from the center. So we apply the switching condition again. Mu kinetic times x2 equals mu static times x1. Plugging in x1 equals 32 centimeters and solving, we would naively get xr equal 40 centimeters. Wow, but wait, that implies the right finger didn't move at all. That's weird. Why did this happen? Because the equation we used earlier was derived for the situation when the left finger supplies kinetic friction and the right finger supplies maximum static friction. To analyze the reverse situation correctly, we must repeat the derivation for the right finger slipping and the left finger static. At the switching point now, mu kinetic times n2 equals mu static times n1, and from torque balance, x1 times n1 equals x2 times n2. Solving these gives the alternate relation. Mu kinetic times x1 equals mu static times x2. This is different from the left finger equation. So plug in x1 equals 40 centimeters, the value used for the reverse step, and solve for x2. After calculating, we obtain x2 equals 25.6 centimeters. This is xr. So the correct switching positions are, the left finger stops slipping at 32 centimeters from the center, and later the right finger's switching position is 25.6 centimeters from the center.